Bismillahirrahmanirrahim. I'm going to summarize the key concept of finding zeros. If you recall, we've suggested before that if you want to graph a polynomial function, you have to find the zeros or the x-intercepts. To do this, we are going to use two theorems. Now, both of these are much easier to apply than to try to put them in algebraic lingo. So when we actually do problems, you'll see they're not as bad as it seems. But there are two theorems that we use in finding the zeros. The first one, which we have already talked about, is the factor theorem. Okay, the factor theorem. I'm going to review this before I go on. And then the second one is called the rational zero theorem. Now, these two theorems are basically how we're going to use, how we're going to go about finding the zeros of a rational, of a polynomial function. Now, the factor theorem, which we already talked about sounds more fancier than it is. If you're given a function, for example, f of x is x cubed minus 8x squared plus 11x plus 20, like this. And let's say if a certain f of, let's say negative 1 is 0, if f of certain number is 0, okay, then, okay, then x minus this number, negative 1 over here, is a factor of the function, is a factor. That's what that means. Now, if you put it in more formal terms, if f of s is equal to 0, if f of some number is equal to 0, then, okay, x minus s, okay, is a factor of course, of the polynomial function we were talking about. So if f of s is equal to 0, then x minus s is a factor of the polynomial function. Okay, so that's what that theorem says, and that's pretty easy, hopefully intuitive to understand. If f of s is equal to 0, then x minus s is a factor of the polynomial function, and we talked about why that is previously. Now, the rational zero theorem is very useful because it predicts all possible, yeah, you heard it right, all possible rational zeros a function may have. Okay, rational zeros. In other words, it gives you like the lineup of numbers. Okay, so you know, if you have the lineup, who are the potential candidates. So it gives you all potential rational or the candidates, okay, for zeros. So you'll have like a whole bunch of numbers to pick from to find out which one is 0. Okay, this is going to be a 0, this is going to be a 0. Okay, this guy is not, this one is not, this one is not, this is not. So the rational zero theorem is very useful because it predicts all the possible zeros, all the possible x-intercepts a function may have. Okay, now remember this. I'm going to erase this in a second, but understand, these are the two theorems you're going to use to find the zeros, the x-intercepts of a polynomial function. You're going to use the factor theorem, which is that over here. If f of s is equal to 0, then x minus s is a factor of the polynomial, and then the rational zero theorem, which predicts all the possible rational function. Now, here is an example of a polynomial function. Okay, here is example of a polynomial function like this. Okay, now looking at this, you'll see these are the x-intercepts. Okay, what the rational zero theorem allows, it predicts this. It predicts this. It also predicts a lot of other things, you know, which are not going to end up being zeros, but it gives you the choices to pick from, okay, to try out. Because let's say it predicted the following numbers, negative 6, and it predicts in plus or minus 6, or plus or minus 1, plus or minus 8, plus or minus 10, and plus or minus, okay, 1,000, whatever. So it gives you all of these choices to pick from, and then you can try one of them out at a time using synthetic substitution or whatever, right? So, and then once you find them, you're done. So what it does, it gives you all the potential potential rational zeros, okay, to pick from, and the candidates for the zeros, and then you have to try one of them at a time, and then until you find all of them, okay. Now, more formally stated, okay, if you have a function, if you have a polynomial function such as this, f of x is equal to, and this is a generic polynomial function, a of n to this, and then a of n minus 1 to the x to the n minus 1. This is, remember, a generic polynomial function, to all the way up to a sub 1 to the x to the power 1 and a sub 0. So you recall that this is a polynomial function, and we have said before that this is the leading coefficient, right? And we have said this before that this is the constant term, okay? So that's the constant term. These are going to be the two most important players in this term, okay? So the rational zero theorem says, okay, now for every polynomial that's like this, okay, there's a caveat, okay, fine print that you never read until you're in trouble. The fine print says that all the coefficients have to be integers, okay. Now, this only works for all the coefficients that are integers, okay. This theorem only works for all coefficients. That means you can't use this for a function that's like negative 2/3 x to the 7th and minus x to the 5th, because this is not an integer. But what if it's a fraction? Well, then you take calculus. You know what I'm saying? So, but here we're learning the basics of this. So, this theorem only works for if all the coefficients are integers. Okay, that's one thing. Okay, then it says every rational zero, okay. Now, why is it rational? Okay, that's because, okay, you just said every zero, right? Every x-intercept, right? Right? Why do you have to say every rational x-intercept, every rational zero? The reason is because a function can have irrational zeros. No, as a function can have imaginary zeros. Okay, imaginary zeros. So this theorem does not predict those imaginary zeros. Okay, this theorem is useful for finding the rational zeros. Okay, so it says every rational zero can be predicted. It can be predicted by what? How can it be predicted? You say, well, this is how I remember it, okay? It can be predicted by as follows. All of them are going to be they're all going to be fractions such as factors. This is how I remember it, okay? Factors of the last term, okay, over the factors of the first term, or the leading coefficient, okay? All the factors of this, all the factors of this, and every single rational zero is going to be a factor of this and a factor of this, okay? Where p of the last term, the last term is this, and the first term is a sub n. So all of the rational zeros are going to be some factors of a sub 0, okay? Some factor of a sub 0 over factor of a sub n. I kind of remember it's like the last over the first. The last will be the first, and the first will be the last, right? So it's like this. So this is the rational zero theorem. Now, if it doesn't make sense to you at this point, that's okay, because it's as I say, it's not as hard as it sounds. But let's see that as an example, and that will make more sense to you, inshallah. Watch. So here's a function f of x equals 2x cubed plus 2x squared minus 11x plus 12, okay? So this is a polynomial function, and it's going to have some x-intercepts, right? So we're going to predict the x-intercepts, all aka x-intercepts, okay? It's going to be the zeros of the function, okay? So x-intercepts, also known as the zeros of a function. That's what the theorem is going to predict, rational. Now, they are all going to be, okay, the zeros are going to be factors of the last term. So let's round them up. So let's do this. Factors of the last. Let's write them out. So factors of the last terms are, okay, well, it's 12, right? Okay, so what are the factors of 12? Well, 1 is a factor of 12, 2 is a factor of 12, 3 is a factor of 12, 4 is a factor of 12, 5 is not, okay, 6 is a factor of 12, and 12 is a factor of 12. That's it. Those are all the factors of the last term. Okay, now let's write down the factors of the first term. Okay, and these are, it's easy because the factors is just one. There's only one factor, right? Now, all potential rational zeros, all possible zeros, okay, all the possibles are zeros are going to be the last factors of last or the factors of the first, right? So here they are. Okay, here's the last. Okay, so you can start with 1 and go over there. And they're all going to be plus or minus. So it's going to be plus or minus 1 over 1. Okay, comma. Okay, plus or minus 2 over 1, comma, plus or minus 3 over 1, plus or minus 4 over 1, okay, plus or minus 6 over 1, and plus or minus 12 over 1. Now, if you, in this case, very easy because there's only one factor. So all the potential zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And there you are. You don't have to look for like 200,000 different numbers. You just have to look for 1, 2, 3, 4, 5, 6, 12 of them. You guys just have to try 12 of them out. We're going to make it easy. You can simplify it for you don't have to do 12 times, okay? But what this theorem tells you is a very powerful theorem. It tells you that this is it. These are all the rational zeros. These are all the possible x values. Not all of them are going to be it, but these are all the possible that can be. Most of these are going to be rejects, but you're going to pick them out and you're going to be able to find the zeros from this, okay? I'm going to give you another example. Okay, so they're all pretty easy over here. So let's try this. I'm just giving an easy example. Okay, let's say this is the f of x is equal to 2x cubed, okay, plus 3x squared minus 11x minus 6. Okay, now we want to find all the possible rational zeros, right? Or all possible zeros, okay? Rational zeros, meaning not imaginary zero. So all possible. So all we have to do is do the factors of the last term and factors of the first term and put them all together. So let's do factors of the last term, okay? Now here's 6, okay? So it's going to be it's going to be 1, and it's going to be 2, and it's going to be 3, and it's going to be 6, right? And you don't have to worry about plus or minus because in the end they're going to be plus or minus. Okay, now we have factors of the first term. In this case, it's 2. It's going to be 1 and plus or minus 2. Oh, sorry, 1 and 2. Okay. Now what you do is all possible zeros. So here's the possible zeros. Okay. Now you're going to have to test them all out, see? But here's at least a list of all potential zeros, okay? So factors of last over first. So you're going to take this one and put it on here. Take this one, put it on there. Take this one, put it over there. Take this one over there, okay? So, and these are all going to be plus and minuses, okay? Plus or minus, okay? 1 over 1, 2 over 1, 3 over 1, 6 over 1. And this is going to be plus or minus. Plus or minus, plus or minus, plus or minus, and then it's going to be 1 over 2, okay, plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 6 over 2. So 1 over 2, 2 over 2, 3 over 2, and 6 over 2. And you can simplify this. It's going to be plus or minus 1, okay, plus or minus 2, plus or minus 3, and plus or minus 6. And here you can simplify these as plus or minus half, plus or minus 2 over 2 is 1. We already got that, so right, you already got this one, so you can erase that. But plus or minus 3 over 2 and plus or minus 3. It's also redundant, okay? So these are all the potential factors, potential zeros, and then you have to try one at a time. Okay, so I'm going to review, and then I'm going to start, and then I'm going to finish, and we'll continue next time, inshallah. So in finding zeros of a polynomial function, we're going to use two things. We're going to use the factor theorem. How? We'll find it next time. Okay, we're going to use the factor theorem, which says if f of s is equal to 0, then x minus s is a factor. Okay, that's what that theorem says. And then today we talked about the rational zero theorem. The rational zero theorem. This theorem says that all the factors, all the potential zeros, okay, are going to be factors of the last term over factors of the first term. And you can see these are all the potential candidates that you have to try. And how are you going to try it? You're going to try it by doing this one at a time. And whichever one turns out to be 0, that's going to be a 0. Okay, so this gives you all the potential candidates, and the factor theorem tells you which one of these candidates is going to work. And that's it. And you can find the zeros for the function. We'll do some examples of this next time. Until then, as-salatu was-salamu ala sayyidina Muhammad wa ala alihi wa sahbihi. Assalamu alaikum.